Next, we will begin the plenary session 2. In the first presentation video, he is Professor Fred L. Mannering, CUTR Executive Director, Civil and Environmental Engineering, University of South Florida. The title of the presentation is Some Critical Data Analytic Issues in Smart City ITS Data Evaluation. Let's watch the video.
So today, I'm going to talk about some critical data analytic issues in Smart City ITS data evaluation. But these fundamental issues that I'm going to talk about today also apply to all transportation data analysis and to, in many respects, to data analytics beyond the transportation field, because there are going to be fundamental elements relating to unobserved factors, human behavior, and so on. So I'm going to get into that in a few seconds. But first, let me look at the need for data analytics in terms of smart city ITS projects. We can think of it, there's at least two important elements. One is that you want to evaluate the effectiveness of an implemented smart city ITS project. So you've done something, it's implemented, you want to know how effective it is. The second one is you can use data analytics potentially to determine the most appropriate and effective smart city ITS project, the one that you should implement. Now, some of the elements that I'm going to talk about in a few minutes are going to expose some of the difficulties in doing both of these tasks, okay? So let me look at the four key issues that I'm going to address in this talk. The first one is unobserved heterogeneity. And I should mention that all four of these issues, I've recently wrote papers on all four of these things. And at the end of today's talk, I'll give you the references so you can explore each of these individually in more depth if you have time. So the first one is unobserved heterogeneity. And unobserved heterogeneity basically arises from the fact that when we collect data, there's always something that we cannot collect, very complex behavioral process or something that we do not collect. So there's observed heterogeneity, which we can look at the data that we do collect and we observe the heterogeneity in the data. But then there's the unobserved aspect of it, the data that we do not directly observe. So I'm going to talk about statistical and econometric techniques that have been developed in the last decade or two that address this issue of unobserved heterogeneity. The next one is going to be data size and the prediction causality trade-off. So in years past, you have a couple thousand observations. That's about the maximum data size that you would get. But in today's environment, you can have hundreds of thousands, millions of observations. So data size is going to limit what analytic approach you use. But there's also the analytic approaches that tend to be very good for large data are not very good at uncovering causality. So they're good for large data, they're great for prediction, but they don't uncover the causal effects. So I'm going to talk about some of the trade-offs involved there. The third point is what I'm going to call temporally shifting model parameters. And really what's happening here is human behavior is changing in fundamental ways over time. So there's sort of a long-term trend in changes in human behavior. And then there's human behavior that would change in response to a project that you built, sort of a localized, immediate change in human behavior. So I'm going to talk about how you might deal with these changing behaviors. And the fourth point that I'm going to talk about today relates to the compensating behavior of users. So what this refers to is sometimes you may implement an ITS strategy to improve safety. And what you find out is that safety doesn't improve at all, or it improves much less than you thought. But the reason for that is that people have compensated their behavior, right? They found that the facility is safer, so they might decide, well, it's safer now, I might drive faster. And so the benefit is not extracted necessarily in safety, but could be extracted with greater mobility. And again, I'll talk about this, give it an example as we move into each one of these topics individually. So the first topic that I'm going to deal with is unobserved heterogeneity. So data collected for the analysis, no matter what analysis you're doing, can never be complete. So there are statistical methods that have been developed to account for the fact that you do not have complete data. You know, an example would be that you observe a vehicle in a crash. You may have information on the driver characteristics, but you don't have the detailed information on, you know, where the impact was on the vehicle, how the energy dissipation happened throughout the vehicle. So there's going to be a lot of things that we're not going to be entirely able, even if you have a fully instrumented vehicle, there's still going to be things that you're not going to be able to entirely capture. So the way that this has been dealt with in statistic and econometric fields has been to use mixing distributions that assume that the heterogeneity that occurs throughout the population can be represented by some parametric distribution. So when we think of the use of mixing distributions, the most obvious one that comes to mind would be what we call random parameters models. So what these models do, instead of estimating a single parameter for the entire population, is they allow the parameter effect of the explanatory variable, the effect of the explanatory variable, to vary across individual observations. So if you go through the transportation data analytic literature, you will see the application of random parameter models in the last 2 decades have become quite extensive. Similar to random parameter models, we have latent class models. So the idea is that unobserved heterogeneity does not necessarily vary from one observation to the next, but there are groups of observations or latent classes that share the same marginal effect or the same parameter values. So instead of having individual parameters per observations, you have groups of people, classes, groups of observations that have the same parameter. The third approach is what I call the Markov switching models. And I've done a couple research papers on Markov switching models. So the idea of Markov switching models is that the parameters that you estimate may vary over time between 2 or more states. Now, conceptually, this is a really interesting idea, but it's very difficult to estimate these models. I have one research project where we use supercomputers to estimate estimating. It's a very difficult estimation procedure, but it's a good conceptual theory, is that you can view observations as switching between multiple states. So all of these models, random parameter models, latent class models, I'm going to refer to these as heterogeneity models. And we're going to come back and talk about these in a few seconds in a little more detail. So what happens if you ignore this unobserved heterogeneity? Well, you can show mathematically that you'll get biased model estimates. You can get erroneous inferences and conclusions. You could say that, yes, the ITS project was effective when it really was not, and your results were affected by the fact that you did not account for unobserved heterogeneity in your data. And as I mentioned, there are common statistical tests that you can use to show that you determine if unobserved heterogeneity is a concern in your data. I mean, you can use like a likelihood ratio test if you're estimating with maximum likelihood methods. So unobserved heterogeneity is the first point that is going to be an important concern in this data analysis. The second one is data size and prediction causality trade-offs. So when you think of ITS data, The size of ITS data can limit the practical use of statistical models. Usually when we estimate statistical models, we're talking about a couple thousand observations, but now we have millions upon millions of observations. So that leads us to big data methods, such as machine learning. However, these methods are notorious because they do not necessarily uncover causality like these statistical and econometric methods can. So this is something that is a concern. There's a trade-off. Big data with machine learning is great prediction, but the causality is an issue. So models that predict well may not uncover causal effects very well. So when we look at the models that have been used in the analysis of transportation data, we have traditional statistical models, heterogeneity models, which I just talked about, data-driven methods, which include machine learning, and causal inference models, which are very popular in economics, but have not been used much in transportation data analysis. And the reason is that usually to control the causal effects, you have to use very aggregate data, so that limits the number of items that you can actually predict. So causal inference models have not been used much in transportation. If we look at the trade-off, this nice diagram that has the trade-off between prediction, causality, and data size trade-offs. So when we look here, let's first look at big data suitability. In this case, the data-driven methods, which are represented by the red line, have very good big data suitability. And they have excellent predictive capabilities, but they're very weak in causal inferences because it's hard to figure out what the causal effects are. When we look at traditional safety models, they have a little bit of predictive capability, not much big data suitability, and they uncover some causality. The causal inference models, which are again mostly in the economic fields, have limited predictive capability because they do not deal with the micro-level data that we need to make predictions in transportation contexts. They have very limited big data suitability, but in very controlled circumstances, they are very effective on uncovering causality. Then there's the heterogeneity models, which have pretty good predictive capability, not to machine learning standards. Some big data suitability because you're using simulated maximum likelihood estimation in most cases, but not nearly as good as machine learning. But you do have a great opportunity here because they do have very good causality. They're very good at uncovering causality. So you can imagine, for those of you looking for research topics, the best analytic method for the future would be some combination of machine learning, which gives this red triangle, with this green triangle, which would be the heterogeneity models. There have been some papers recently that have tried to combine these two methods. It's not necessarily an easy task, but there's a lot of potential there as a way to handle large amounts of data, but still uncover underlying causality. So now let's move on to temporally shifting model parameters. So the issue here is that human behavior is continually evolving. And this human behavior continually evolves for many reasons. There's just natural evolution with new technologies being introduced, not just in transportation, but societal effects and so on. And you can even view the pandemic as an evolution of human behavior. So there are long-term structural shifts that are induced by continually evolving behavior. And when I wrote this, I wrote a paper on temporal instability for the safety field. This paper looked at a lot of the cognitive literature and from neuroscience and so on. There's a lot of science that goes beyond why human behavior is changing, and that the change has accelerated greatly in recent years. So in the transportation perspective, there are behavioral shifts that are induced by technological innovations. And you could look at it as there's, with all the new vehicle technologies that are coming forward, it is is resulting in a fundamental change in the way humans drive cars. Okay, so when we look at temporal instability, there's ample evidence from safety and travel behavior literature of the parameters changing significantly from one time period to the next. And there are standard statistical tests that can be applied to show why this is the case, like a likelihood ratio test if you're using maximum likelihood ratio. So if you're using maximum likelihood estimation. So ignoring the temporal shifts that are likely occurring in your data can lead to erroneous conclusions and inferences. So it's very important to think about when you're analyzing data. If you have data that's collected 2 years ago, using that data to predict what's going to happen today could be problematic. And that's something that you can explore empirically, looking at the concept of temporal instability. The last point is compensating behavior. So we can look at this as that the introduction of innovative technologies, which is going to be, smart cities and ITS for sure, and also semi-autonomous vehicles. There's a lot of applications for this. It's going to change behavior in unexpected ways. And the example that I'm going to use is consider a technology that improves safety. What will happen? So you have this little diagram here. So we can say that in some initial phase, there's a trade-off. Individuals are making a trade-off between what I'll call driving intensity, which could be speed or driving distracted. I'll refer to all of those elements as driving intensity, and the probability of a driver avoiding an accident. So the way to look at this is that each individual driver has some equilibrium point where they say, okay, I'm going to drive at a speed that gives me like a 1 in 10,000 chance of getting into an accident, because that's my acceptable risk. And that acceptable risk would be represented by this point A, where you're trading off how fast do you drive, or how distracted do you drive, and what is your probability of avoiding an accident. Now again, each individual person in your data set will have a different point A. So now if we do a safety improvement, an ITS safety improvement or something in the smart city that shifts this equilibrium, so this line, the line which has the marginal rate of transformation moves to the right, and the expectation that analysts often make is that people will retain the same driving intensity, and that we're putting in this project to improve safety, so all the benefits will be for safety and we'll move to point B. In another extreme case, you could say, well, if a person completely compensates, it's like I want to have a 1 in 10,000 chance of getting into an accident, I keep my 1 in 10,000 chance, I'll move to point C. So we'll have no effect on safety. Your safety improvement will have no effect on safety, and I'll just start driving faster or driving more distracted. Now in reality, the points are somewhere going to be probably between B and C, something like point D. In an extreme case, though, you could have someone that grossly overestimates the safety effectiveness, and you could end up in point E, where you're driving faster and actually reduce safety. So keep this sort of compensating behavior in mind when you're trying to understand what's going to happen to an improvement that you implement. So if we ignore compensating behavior, you'll lead to an overestimation of the intended effectiveness of the safety improvement in this case, and unexpected consequences will arise that you have faster drivers, more distracted drivers. But you should have anticipated that by recognizing that compensating behavior was a possibility. So to summarize, the transportation field has entered an era of unprecedented technological innovation. When you think about what has happened in the last 4 or 5 years even, it's been amazing. So many things are happening. The data analytics face key questions that limit their effectiveness in the evaluation and forecasting of smart city and ITS. So these are the 4 examples that I gave here. So researchers must think about unobserved heterogeneity, the implication of analysis methods, let's get to the big data prediction, causality trade-offs, temporal shifts in behaviors, and compensating behaviors. So again, The papers that discuss each one of these topics are listed here. I have a 2016, 2020, 2018, and then the compensating behavior paper that I wrote in 2006 that looked at how people traded off when you put in anti-lock brakes and airbags. I've since applied that paper to the new technologies that we have today. So think about these four elements, glance at these papers if you prefer, and have a great time analyzing data because we're entering a great period. Thank you.
Thanks, Professor Manori. Next, we will watch the video from Professor S.C. Wong, Engineering, the University of Hong Kong. The title of presentation is Calibration of Stochastic Link-Based Fundamental Diagram with Explicit Consideration of Speed Heterogeneity. Let's watch the video.
Hi, everyone. Good afternoon. My great pleasure to present the paper here in this conference on calibration of stochastic link-based fundamental diagram with explicit consideration of speed heterogeneity. Here are some of the collaborators of this work. First, I would outline the presentation. First, I give the background and discuss the model formulation. Then I would give a case study to show how the model works, and also discuss the heterogeneity effects for the case studies, and also what the conclusions at the end. As you know, the fundamental diagram is the basis of traffic flow theory, and has been a long history. And most of the work is based on a single regime model with a single function describing the whole density range, and also multi-regime models. And both of them establish equilibrium speed density relationship with a strong assumption that each density would correspond to only one deterministic value of the mean speed. However, if one looks at the empirical fundamental diagram of road traffic, you see there's a certain scattering, certainly the inherent uncertainty exists in this microscopic traffic flow model. The heterogeneity effect can come from the traffic environment, the road condition, vehicles, drivers, driving behavior, etc. And so, as you can see from the diagram, the mean speed and flow rate actually vary substantially for given density over a finite range. So the question is how to model this uncertainty, explaining this, how the data scattering around the mean values, and also how to incorporate physically relevant random variable into the model structure. So here, to answer these two questions, first, I would try to establish the stochastic structure to incorporate the variables that represent the uncertainties, and then establish a stochastic link-based fundamental diagram. Here, I'd like to explicitly considering the heterogeneity effects. So there are two sources we kind of available. Okay, the first is the speed heterogeneity. Even at the same density, the speed would expectedly vary. And this speed variation actually be available in many traffic sensors, but they're largely ignored and not used in the analysis. After collect data, they get the mean value, and then they just throw away this very useful and meaningful data. The other one is the rainfall intensity, which kind of represent the traffic and the environmental conditions. And then there are also some unknown sources like traffic incidents, strong winds, and so on and so forth. But all this actually be not available in the data source, and so as sometimes they're not modeled. But all these unknown effects will be captured by those error term, general error term in the model. Now let me explain the conventional approach, where you got a road section, you equip with a detector, and then you capture the traffic data, and typically we measure the speed, flow, density, and so on and so forth, and then we establish the model, and then we state the traffic speed, the mean speed, as a function of density and environmental factors like rainfall intensity. And there's an observable component, which you know the data so that you can specify this function. But obviously, they are not exactly equal. So generally, we add the error term, okay, to account for those unobservable factors. Now, the question here is that even at the ideal condition where you don't have error, okay, under a very perfect situation, so you get a sensor. Well, when you observe the traffic passing through, okay, well, actually, you will collect the speed information of individual cars. Okay, they would obviously vary, among the driving population. So therefore, even under this perfect situation, you will repeat the measurement again and again. So you would not get exactly the same mean speed, because from statistical theory, we know that the mean speed collected at this particular location, okay, there would still be a certain variation. And this variation can be estimated because we know the variability of the speed and we know the sample size. So therefore, we can actually establish this distribution of mean speed, and this is actually known information. And as I said before, this information generally ignored, okay, and not utilized in the development of the theory. Now here, what I try to do is to make full use of this information, okay, from the detector. So we can then specify the model. As you can see, okay, even under ideal situation, there's not like a single value of the mean speed, but they follow the distribution. So therefore, it's natural that we would specify the function here on top of the deterministic observable component to represent the distribution due to speed heterogeneity in the long run. Okay, if we repeat measurement many times, then to expect the speed will also follow certain distribution, okay, due to the variability of the speed population. And then, in the general sense, we would also add the general error term into the model. Now, compared to the conventional analysis, okay, the main difference is that we establish this, implicit speed heterogeneity function into the calibration procedure for the traffic flow model. Okay, first, let's look at this speed heterogeneity effect. So this is the variance, okay, but we know the mean speed variance is equal to the population variance divided by the sample size, but the sample size is known because from the data collection process, you on top of the individual speed, you also capture the number in the sample. So in that sense, we would be able to use the data, the sample data, to estimate the population variance and then divide it by the sample size, and that was the expected variation of the speed under the speed heterogeneity conditions. So what I do here is that I try to establish this variance as a function of density and rainfall intensity. K stands for density, represent the traffic condition, and R, the rainfall intensity, describe the environmental factors, and beta are just the parameters. Okay, so in this case, I can then specify the function U bar as the mean speed for the detector as a function of density and rainfall plus this speed heterogeneity function. And this function follow a normal distribution of the mean zero and the variance governed by this established function. Now, here is the flow chart showing how we model the stochastic structure. So first, we have the known heterogeneity. So these are like the rainfall, the speed heterogeneity from the traffic detectors, and so we establish the function, and these are known. Okay, there were also unknown heterogeneity. So we use the unobserved heterogeneity across the mean speed, okay, and then we use the random parameter structure on the model parameters to describe this unobserved heterogeneity, and then the rest, the data noise, is governed by the general error term. So by combining this, then I have this stochastic link-based fundamental diagram with this implicit consideration of speed heterogeneity here and the error term, and that becomes the function. So let's look at the case study to demonstrate how it works. Here I got two traffic detection zones, and these are the general data. We observe 1 full year data, and then we divide into every 2-minute sample. So that's why we have quite a big sample size. And you can see the mean speed of these two are different. And also the speed heterogeneity, as you see, the estimated mean of variance actually, quite sizable. Okay, so this actually affecting the mean speed. So here the first function, the speed heterogeneity function, but we find that this speed heterogeneity is related to density, and so and the rainfall intensity. So we specify this exponential function, and as you see, right, this is actually equal to the population variance divided by n, and n is related to density because of the sample size. Okay, so this is expectedly related to the density as well. So we expect the speed of free is roughly equal to 1 expectedly, but we allow it to vary in this example. So now, then the general model formulation is like you have this free flow speed and optimal density in the direct model as model parameters of the direct model. The rainfall intensity, okay, the effect is governed by the parameter gamma, and then we have this heterogeneity, speed heterogeneity distribution, okay, and with the variance governed by this implicit equation. And free flow speed and optimal density follow the normal distribution. But in this case, these two heterogeneity variance, unobserved heterogeneity variance, actually unknown. Okay, it's the kind of to be determined by the data. And then we have the general error term, okay, with a known variance. So all the mean speed at 2-minute interval, and the rainfall intensity, and so on and so forth. Now, we establish the model using this two-stage process, hierarchical process. In the first stage, we assume this heterogeneity, speed heterogeneity variance, okay, is calibrated from the data set as a function of density and rainfall intensity. And then with this as then upper level input, we put it into the lower level, the hierarchical Bayesian model, okay, with the mean speed and variance of the mean of the free flow speed, the mean of the free flow speed and variance of free flow speed, mean and variance of optimal density, number associated with rainfall intensity, and the general error variance are all estimated by the Bayesian model. With the input of this speed heterogeneity distribution, input into the second stage model. Now, although it's a two-stage model, but the calibration parameters actually conducted simultaneously. So to compare the result, we established 4 models. The first one is the fixed parameter model. We don't consider variance for the 2 parameters, free flow speed and optimal density. We take it as less fixed parameter. But in this case, we consider both 2 models to see the effect of speed heterogeneity data. So we first model, we do not input the data of speed variation. And then the next model, although it's fixed parameter, but we input the speed heterogeneity function, okay, which to collect data, and also add one more term here. Now, and then we consider 2 more models, okay, by assuming free flow speed and optimal density are random parameters, okay, with corresponding mean and variance. Okay, again, we consider 2 cases, one without speed heterogeneity, the other one with explicit speed heterogeneity function. We would compare the results using the DIC to see their model fitting, and then we also try to look at the variance of the general error term, okay, which associated with how much unexplained factors have actually be represented into this error term. And so the smaller the variance, the better, because that means that most of the variance structure has been explained and described by the model structure. And also we try to use a K-flow cross-validation procedure, okay, to test the model prediction. Like every time we take out one set of the data and use the rest for calibration, and then predict the numbers for the independent data set, and then we can evaluate the MAPE because the data is not embedded into the calibration, so it's can be used for validation purpose. So here's the calibrated results, and it's good that all the model parameters are statistically significant at 5% level. And as you see, the parameter are all reasonable with the free-flow speed, okay, around 80 and 67, whereas similar to those data obtained when the traffic condition is free-flow, and the rainfall kind of negative effect on the speed, and that's also very reasonable. Okay, and here is a comparison. First, we look at the DIC value. For DIC, of course, these two columns cannot be compared because one with additional speed heterogeneity data, and so we just compared the situation where you do not have this additional speed heterogeneity data. So we look at the random parameter models actually much fitting better than the fixed parameter models in general. Now for us, two models with speed heterogeneity data, we find again the random parameter models also fit better than the fixed parameter model. So generally the random parameter model is performing better. And we look at the general error term. As you see, compared to the four models, the full model random parameter with the speed heterogeneity will achieve the smallest total random error. Okay, so it's fitting much better. Now we look at the cross-validation results. So we divide the data set into 12 sets, and every time we use 11 sets of data for calibration, and then predict the last independent set, and then we calculate the MAPE. So as you see here, generally, so the random parameter model is having better performance, their prediction performance than the fixed parameter model. As you see, the lowest MAPE mostly in the last two columns of the two sites, and also the effect of heterogeneity. The consideration of this speed heterogeneity will also have a better prediction results, and generally you see with speed heterogeneity data you can have a better lower error in the prediction. So you can also see the random parameter model generally perform much better, okay, than the fixed parameter models. Now for the heterogeneity effect, you can see here. There are actually three heterogeneities. One is the general random parameter. We will capture the heterogeneity effect, okay, which is an unobserved heterogeneity effect. And then the second is the implicit speed heterogeneity from data, and then the last term is the error term. And so here is a summary. As you see here, even though you look at two different sites, okay, but as you can see, the speed heterogeneity will actually be accounting for around 20% of the total variance. So it means that they are actually very valuable information. Those are available in the traffic detector generally, but people don't use it and don't utilize this data. But actually, it's very useful. Can explain like around 20% of the total variance. As usual, the random parameter model is actually best representing the unobserved heterogeneity. And here you see we also capture almost half of the total variability. So here's the look at the rainfall effect. As you see here, there's a common sense that during the raining days, the general speed will actually fall. Okay, and here in this model, we were able to capture this effect. Every 0.5 millimeter increase in rainfall intensity with our effect will reduce the free-flow speed by around 8 to 9 kilometers per hour, and also at the optimal speed will also decrease by about 5 kilometers per hour, and this is quite substantial. Okay, so as you can see here, as I said, like the speed heterogeneity would account for around 20% of the total variability. And the use of random parameter model can also capture around half of the total variability. And generally, the variance of the random parameter model with the speed heterogeneity, okay, would best describe the effect of the stochastic, the scattering traffic flow data on the diagram as a function of speed, as a function of density and rainfall. And here the model will be able to provide a more complete information of density and rainfall intensity than the other models. And with the observable and identifiable information, the model prediction of the proposed model also much better than the fixed parametric model and also the one without speed heterogeneity data. Okay, so making the fundamental diagram more explainable. So as a conclusion, here we propose a novel stochastic link-based fundamental diagram with explicit consideration of speed heterogeneity. Okay, we explore the random parameter structure to model the unobserved heterogeneity effect. And we propose a two-stage Bayesian model for the calibration of the proposed model. We also find out the effect of rainfall intensity on the mean speed and free flow speed as well. As a further research, okay, we try to explore other effects like the traffic environment, traffic conditions, road design, etc., and how does affect the uncertainty of traffic flow. Okay, and also generally, in many cases, the data will actually be coming from different sources with different resolutions. I think it's a challenging topic how to study the stochastic fundamental diagram with multiple data sources, okay, with different resolutions. Okay, and that's all for my talk. And any questions are most welcome. Thank you.
Yeah. The next presenter is Professor Karong-man. He is technology Chiang, Jiaotong-Liverpool University, Suzhou, China. The presentation title is Deep Learning in Video Anomaly Detection and its Application. Let's watch the video.
Welcome everyone to this special lecture. I'm Karong-man from Xi'an Jiaotong-Liverpool University in China. Today, I'm very happy to be here to share our experience on deep learning in video anomaly detection and its applications. In this presentation, first I will present the research background of our work over the past few years, and then I would like to show you what we have achieved in the past few years, then end up with a short conclusion and point out direction for the future works. So number one, we will discuss a little bit the research background. We do research on deep learning. So actually, over the years, okay, we moved from AI, artificial intelligence, to deep learning. So now I start to present something about the AI. For sure, many of you are very familiar with AI. Actually, AI, artificial intelligence, is intelligence shown demonstrated by machine. And then machine learning. Machine learning is a study of computer algorithms that can improve automatically through experience by using the data. Deep learning. Deep learning is a part of machine learning based on artificial neural networks, ANN. Actually, there is a roadmap from AI to deep learning. We start with AI, and then after that, we move to machine learning. Recently, we moved to deep learning. Here, I have a picture to show the relations between AI, machine learning, and deep learning. We can consider AI is a superset because AI was developed since many years ago, consists of machine learning. And then we moved on from machine learning, we reach deep learning. So artificial intelligence is a superset which consists of machine learning. And then machine learning consists of a subset of deep learning. They all are linked together. So we can find many similarities between AI and machine learning and deep learning. So we take a closer look at neural networks. Again, I know many of you are very familiar with neural networks. Okay, we start with ANN. ANN is a kind of computer system inspired by biological neural network that build animal brains. We start with the convolutional neural network. Okay, the network are arranged into layers. And then we move to recurrent neural network, RoNN. Here we introduce the temporal information, okay, into the network. Recently, we have also two-stream CNN model. Actually, it's an extension. We have two streams. One is for the spatial stream. The other track is for the temporal stream. So for the two-stream CN model, which consists of two tracks, one is for the spatial one, the other one is for the temporal one. So far we know there are some limitations of the current models. Examples, in CNNs, only spatial features can be attracted by CNN. This is not ideal because there is no temporal information, temporal features. RoNNs, the best known one is the LSTM. It is called a long short-term memory. LSTM requires a more computer power than CNN, so power consumption. And then LSTM cannot handle high-level motion in the video. The last one is two-stream CNN. As I said already, we consider two tracks, spatial and temporal. Due to the limitation of computing power, CNN structures in two streams are not very effective, are not really advanced. The process of generating optical flow is also affected by the moving of the camera involved. So far we know there are so many applications of AI or using AI. For example, in computer vision, driverless system, image identification or detection or object detection. Our research will focus on video anomaly detection. In addition, AI is widely used for NLP. NLP stands for natural language processing. Example, online translation. This is Chinese, okay, means the weather is nice today. Okay, or for the natural language generation, we can find so many applications of AI in many different areas. Also in the IC design, integration design, and solar energy, and computing, so on and so forth. So now we're talking about our main research aim. We focus on video anomaly detection. Actually, it is a topic or problem detecting unusual event in videos. Here, unusual event, we refer to some unforeseeable event. We can say like this, okay? Example, heavy raining, robbery, serious car accidents, or fire, typhoon, whatever. Something we don't expect, it happens. I would say in any city in the world, there are so many CCTV for monitoring. They are already good, but they belong to the traditional method for video analytics because using CCTV or other traditional method for video analytics all the time require professional people, human beings, to monitor the video constantly to find out some abnormal or unusual, unforeseeable event. This means that it will take away plenty of time. Doing something might not be useful. As a consequence, it leads to a time-consuming task. On the other hand, for some unforeseeable event, we can use a sensor to detect, example, smoke, fire, or humidity sensor, but they are so costly. Also, when we do this kind of sensing using the sensors, okay, usually we don't use one sensor, we use many sensors. So at the end of the whole story, it will be very costly. Okay, now I would like to share our research experience, also our contributions over the past few years. In principle, video classification task is the ideal task to evaluate the general performance of a video handling models. Clearly, in our case, we focus on unforeseeable events, as I said already, fire, car accident, robbery, heavy raining, so on and so forth. In general, two-stream model is chosen because the basic structure is unique. Also, it covers both spatial and temporal information features. However, for long-term videos, the traditional two-stream CNN structure is not handy enough, cannot achieve very good performance. Then we have the following research questions. Number one, how to employ the deep learning architecture in the first stream of the two-stream model to improve extracting temporal features. Second question, how to develop a video pre-processing method in order to improve the quality of the frames inputted. The limitation of the previous research or previous models. Usually, the temporal features are extracted from optical flow. The traditional two-stream model wastes the temporal information in the red, green, blue frames. In addition, the distribution of the sample frames is a little bit random, a little bit unreasonable random. Due to the above mentioned, we have developed a new video processing sampling method to improve the distribution of the sample frames. We also use the LSTM-based model to replace the traditional CNN in the first stream. Therefore, more temporal features can be captured from frames. Finally, we have also implemented a denseless structure to improve the performance of the second stream. So this is our proposed improved two-stream based model for video classification tasks. So the left-hand side, we introduced the LSTM base, to improve the distribution of the sample the frames. On the right-hand side, on the right track, we implement a dense net structure to improve the performance of the second stream, referring to the optical flows. And then clearly at the end of the whole story, we do the fusion. We merge both together. In order to verify or to test our method, our model, we have done many experiments. We used the following data set, UCF, the classical one, the benchmark one, all the people they use, and then FireSense database. Also for testing or for experiment, we have created our own merged data set. Later on, I will present the experimental result together with the pictures, to show the accuracy for our proposed model is better than the existing models. I will present the experimental result for all models developed in our research since the past few years ago at the end of this presentations. This is the paper we wrote related to this improved two-stream based model for video classification tasks. In addition, we have also developed a new new two-stream structure for anomaly detection in videos. Basically, video anomaly detection is a task of detecting unforeseeable events or anomalies in videos. Example, someone is stealing a car, suddenly there is a fire, so on and so forth. So we have the following research questions. Number one, how to improve the ability to extract temporal features from the RoadDB frames. We know unforeseeable anomalous event happens with a very tiny probability. So this makes a little bit difficult for us, to apply data set, for testing, because the unforeseeable event or the anomalous events happens with a very tiny probabilities, very low chance. In addition, due to the potential increase in model complexity, nowadays the model is very complicated because of the speed involved in the video and the color and the quality, so on and so forth. How to develop a better video processing method is also a hard task. The limitations of the current research, actually there's no effective video processing method to handle a large number of video. Also, most of them, I would say, lack of temporal features. They only put in the spatial features. Our contribution are as follows. We introduce a CVD structure before the LSTM in the first stream to handle the low-level temporal features extractions. And then clip-based video processing method has been developed to solve the problem. to improve the problem of the computing power. So if you take a look at this block diagram, the inputs the same as the video. Okay, we have two tracks because all the time we are talking about two streams. On the left hand side, we introduce CVD structure to handle the low level temporal features. Okay, the right hand side, the same as before, we use the dense LED. But anyway, we have also introduced the clip-based video processing method to solve the power consumption issues. So now we take a closer look at CVD. Actually, CVD is a classical model which extends the traditional CNN. Comparing with the 2D one, the 3D one can extract temporal information by additional dimensions. What we do in our model divides each video into clips, okay, one by one, and extracts the CVD features before passing to the LSTM. Since the inputs of the LTSM are feature mapped from CVD, the length of the inputs has been decreased a lot. As a consequence, the final accuracy has been improved. Also, we have done many experiments based on the dataset UCF crime. Okay, again, I will present all the experiment result along with the diagram, picture, full chart at the end of this presentation. Okay, we refer to these two publications, referring to the new two-stream structure for anomaly detection in videos. In order to enhance the applicability of our proposed development methods, okay, we have also developed another application. It is called the Enhanced Public Video Person EPVP system. We know already CCTV cannot be used, I would say, everywhere because due to the piracy or the availability of the network or power or location. We have developed a system using deep learning method, okay, to achieve better video anomaly detections. This system consists of the following, consists of the four components. The first one is a smartphone, okay. So the key idea behind is anyone has a smartphone can upload and send the video, okay. So we start with a smartphone app to be used by authorized user to send videos. And then the video will be received in the video web server, okay. So the authorized user can upload the video, okay, in the server, okay. We do the management of the uploaded video and processing. Also, example, now I see a fire, okay, I see a robbery happens, okay, I am a person, okay, so I'm an authorized person, okay, I take the video of this robbery and then I send this video immediately. The video can be on the fly, also a uploaded video. Look, both options are fine for our system, okay. So in the police station, the officers, policemen, okay, just open a web-based portal, okay, to be used by authorized user. Example, officers or policemen, they can watch the video, okay, and obtain the detect identification result from the video server. This step is automatic. This means that in the video web server, the server will identify, detect what kind of event is, example, robbery or fire. Please note that the whole system does not require additional device to achieve its desired target because we just need a mobile phone or iPad, whatever, to send a video on the fly or upload video to the server. And then in the server does the processing and does the identification, and then to tell the officers, the authorized people, okay, in the police station, in the workstation, through the web-based portal to identify what the event is about, what the anomaly event is about, and then all the process is automatic. Okay, so take a look here. On the right-hand side, we see more or less, okay, our smartphone app, okay, we can upload the video, okay, on the fly or just a video. Both options, okay, are supported by our system now. Okay, here are the papers related to the development of the EPVP system. Also in the paper, we have some, I cannot say it's a demo, some detailed explanation how the system works and example. Okay, now I'm going to show you a demo how our system works for the video uploading and the video identification for anomaly events. Okay, please take a look at this demo together. Okay, the student pick up a mobile, okay, smartphone, okay. Although it is in Chinese, but it's no problem. Okay, we have the subtitle in English, okay. So we transfer a video, okay. So the first thing, we record the video, okay. Okay, just the keyboard, okay, and then immediately we can upload to the server. So in the server, okay, for example, if the video is a file, okay, so the system will identify, or the people in the workstation can watch the video or download the video, okay, and then the server, okay, and then identify it is a file and then report to the people sitting in the workstation. Okay, all process is automatic. It doesn't require any person to identify, to detect what kind of event is, what kind of anomaly event. Currently, we can deal with robbery, we can deal with fire. In the future, we will be working also for the heavy rain and car accidents. Okay, it comes to the conclusion of these special lectures. The current method or current development for the video anomaly detection have the following limitations. Previous deep learning method can hardly consider both spatial and temporal information in the video. There is no system for monitoring and detecting different anomalies. So we have proposed the following solutions. We have developed a new two-stream structure that can be used to improve the temporal feature extractions based on a new LSTM-based model using CVD plus LSTM or together with dense nets. Okay, I have already presented in the previous slide. Our new method, actually two methods, can be used to solve the problem of computing power and generate better input frames. In addition, we introduce a new application, EPVP system. We have seen from the demo, can be used to upload the video anywhere in the city, okay, to the authorized agent for identification, what kind of anomaly events are. So I would say our research has the potential to impact, okay, due to the new processing methods and its structure. Our proposed model can achieve better performance than the previous method in video classification and anomaly detection tasks. Later on, I will show the experimental results. Also, we have introduced a new EPVP system. It's very low cost and very simple, okay, to improve the ability of using CCTV in our smart city, because CCTV cannot be used anywhere because of the privacy, location, and the power network connection. Okay, our future work. In the future, we aim to do more experiment using different data sets. Currently, we are using only a number of data sets, UCF and some fire sands, okay? So in order to have a better understanding of our approach, okay, in the coming future, we aim to apply more data set for experiment and testing. And then we consider to develop a transformer structure, also improve the fusion layer, and then consider to decide the combination of the CVD and the STM together in order to obtain better results. Okay, now I'm going to show you as some of our experimental results for video classifications. Due to our proposed model, okay, I would say if we compare here, okay, our model in general is better than other existing model. Okay, example, against VGG16, LessNet 101. We are talking about the performance comparison of different models in the second stream of two-stream model. Also for the first stream of two-stream model, okay? And then here, the accuracy, okay, of our model. You can take a look here. I would say it's better than all other existing models or method, okay? But if you just take a look at the number, few percent, might not be very significant, but in our field, computer vision, okay, few percent is already I would say, a good improvement. So in the coming future, we try our best to improve more. Also, you take a look here, okay, the performance comparison of different methods on the merged data set. As I said already, we have proposed, we have created a new merged data set for testing. Also using our method, okay, we can obtain better accuracy. Also, regarding the true positive way and false negative way, our proposed methods, okay, also better than the others. Okay, finally, okay, we take a look here regarding the evaluation matrix on ROC curve. Okay, also our method shows it is better. If you take a look at the percentage, okay, our method is better than all the others based on a UCF crime data set. So it's a time to conclude my presentation. I just want to say thank you for listening. If you have any questions, please feel free to send me email, okay? We are happy, I'm happy to share our experience or what we know, okay? Maybe we can develop some further cooperation together. Once again, thank you, the organizer, the conference, okay, has invited me to give a special lecture here. This experience is very important, it's very useful for me. Once more time, thank you for listening. Hopefully, in the coming future, we can see each other on site. Thank you.
Thanks, Professor Karongman. Thank you for watching the video. Next, the final presenter, Professor Xi'an Nipon. He is Associate Professor Electrical Engineering, Chiang Mai University, Thailand. He's a
Hi, the participants of KITS International Conference 2022. This is Nipon Theera-Umpon from Chiang Mai University. It's such a great honor to be a speaker today. And the topic of my talk is on the smart healthcare, an important component of smart city. This is the outline of my talk. I will give the brief information about biomedical engineering, and after that, I will talk about smart healthcare. Emphasizing on AI and digital technology. And I will give the information of my lab, the so-called Computational Intelligence or CI lab at Chiang Mai University. And we will take a tour of the applications of AI to the health-related applications at my lab. And that's going to be only for the brief information. If you have any question or any comments, you may send me email afterward. I will finish up my talk with the final words. What is biomedical engineering? Biomedical engineering integrates physical, chemical, mathematical, and computational sciences and engineering principles to study biology, medicine, behavior, and health. Okay, so this kind of discipline of engineering would develop innovative biologics, materials, processes, implants, devices, and informatics approaches for the prevention, diagnosis, and treatment of the disease. And at the end, we would like to improve the health of human beings. These are some of the BME fields that you might be familiar with. The first one is the biomedical instrumentation, and this is the one that I believe we are most familiar with. And for the rest of that, some of you may be familiar with as well, like biomaterials, biomechanics, medical imaging, bioinformatics, AI in medicine, okay, orthopedic, bioengineering, rehabilitation engineering, infrastructure, transportation for healthcare, etc. So let's take a look at the AI, which is going to be the important part of the smart healthcare. So first question is that, is it worth considering for AI? If we try to Google search that this is what we will come up with, and that's going to be more than 2 billion results coming back. So it means that this keyword is of interest of a lot of people. Okay, and on top of that, if we look at digital signal processing, which I think it is the root of the AI technology nowadays. If we try to Google search the keyword of digital, this is what we will come up with, right? And that's going to be more than 1 billion, okay, coming back for the result of the search. So it means that both of the AI and digital technology are of interest of a lot of people. Going back, okay, about 75 years ago, that's going to be the information theory by Shannon. The idea is that we have information sources in different forms. How can we convert them to a common simple form? Okay, that's the idea of Shannon. And at the end, this is what he came up with, right? From different sensors, different kind of like imaging or signal acquisition, we convert all of them to a common and simple form of 0 and 1. Okay? And it means that it's going to be easier to process or to be used in the transmission of the signal. So when we talk about digital technology, we would have heard about 3 keywords. The first one is the digitization. Okay? When we talk about digitization, we would talk about the raw data, the conversion of the raw data from analog form to digital form. And the second one is for the digitalization. That's going to be about the actual process, okay, that the digital technology can induce the change within industries. And the last one is the digital transformation. When we talk about that, it's going to be the overall effect, okay, to the society. So that's going to be called digital transformation. Okay, the fast development of the digital era, it came up not just recently, right? But it came back a lot more years before. And this is due to the super fast development of the digital devices, as you may see here, right? The number of transistors keep growing, okay? The how we take care of the computations, all of those are really fast in the development, okay? And if we think about the number of IoT connected devices worldwide, you may see that up until now, we might have like about 40 something billions devices, okay? And as you may see here as well, the growth is going to be exponentially, right? It's not just linearly, okay? So it's going to be rapidly grow. So the digital era changed a lot of things, not just the hardware, right? It's not just the devices or the electrical appliance that we have in daily life, but it also changed our behavior, right? Just like the meeting that we have right now, right? It's all online, okay? And this is the result from the development of digital technology. So when we talk about human and artificial intelligence, these are some analogy that we can make, right? Human would have the senses as the input, and also the artificial intelligence would have the sensors or the data as the input. For the human beings, we have brain, right, to process the data, the input data. How about the AI? AI would need algorithms to do that, okay? So it's not just the program, but we need to develop algorithms for that, okay? And the program would come afterward. For human beings to take action, we have the embodiment, right, as the output. And for the computer, we may use the robot embodiment, or we can use the display of the computer for this task. At Chiang Mai University, we have the so-called Computational Intelligence Research Lab, or CI lab. When we talk about computational intelligence, I would like to refer to the IEEE, and we have the so-called IEEE CIS, or Computational Intelligence Society there. And the scope of the CIS is like this. Right? The field of interest of the society shall be theory, design, application, and development of biologically and linguistically motivated computational paradigms, emphasizing neural networks, connectionist system, genetic algorithms, evolutionary programming, fuzzy systems, and the hybrid intelligent systems in which these paradigms are connected. Okay, so this is the scope of the IEEE CIS. And when we talk about computational intelligence, we would have heard three keywords like this: neural nets, fuzzy sets and system, and evolutionary computations. And as you may see here, when we talk about neural networks, that's going to include multi-layer perceptron, support vector machine, deep learning, and so on. And when we talk about fuzzy sets and system, that's going to be include fuzzy logic, fuzzy systems, etc. And for evolutionary computation, that's going to include genetic algorithm, particle swarm optimization, Kaku search, BAT algorithm, something like that, right? And so on. Okay, and this is going to be the comparison of CI and AI. When we talk about CI, we would consider the soft computing techniques, while AI would use the hard computing techniques. When we use CI, that's going to follow the fuzzy logic, while AI would follow binary logic. For CI, we would use nature-inspired models, while AI would use the mathematical models. Okay, and CI is going to work for the inexact or incomplete data, while AI would need the exact data. AI is not going to be very effective on this kind of data. And for the results, CI would give the result as the probabilistic ones, while AI would give that in the form of deterministic ones. Okay, so at the end, we would like to take a look at some applications that we apply to the health, medicine, or biology, okay, at CI lab. So for the signal reconstruction, we have the algorithm that we use to reconstruct the ECG, okay, or the heart activity signal by using linear prediction, just like this. If we have the ECG signal and we miss that somehow, we can come up with the reconstruction. Okay, the red one is the reconstructed signals, and like this one as well. Okay, when we have another signal lost, this is the one that we can come up with the reconstruction. Okay, we also have another kind of reconstruction. For example, usually for the so-called 12-lead ECG, we need 10 electrodes, but in this case, we would like to get rid of 4 of that. And we will try to predict, okay, by using the reconstruction model. So we can reduce the number of electrodes to 6. Okay. So this is the output of the reconstruction. The top one of each of these, V2, V3, V4, V5. Okay, the top ones are the actual signal, and the bottom one are the reconstructed signals. As you may see that we can nicely reconstruct the signals back. This one is for signal extraction or recovery. So we use the automatic algorithm to extract the signal that we measure from mom's womb, okay? And at the end, we can separate the EKG or ECG of moms and the fetus, okay, in mom's womb. This one is very important if we can measure the ECG of fetus indirectly, okay? And we also work on the classification of the EEG, which is the brain signal. So we can measure the brain signal and we can classify what the subject is thinking of about moving his or her hand, okay, on the left side or the right side. Okay. We also have the fall detection system that we would try to detect the fall of the patients or the elderly. So we can classify the fall from the other activities like sit down, stand up, or jump, or running, walking, something like that. We also have the fall detection system based on image. So that's going to be another one that can be applied without any sensors on the subject. For human-machine interface, we have the automatic lip reading system that use camera. So this is for the patient who cannot move his body at all, but just the lips. So he or she can move the lips, and we will try to interpret that. Okay, we have about 15 words that most frequently used in the hospital. Okay, and the patient can communicate with the medical personnel. For the patients who cannot even move the lips, we have the eye gaze tracking system in which the patient have his eye gaze on the screen and the pointer would be there. And if the patient stare at that point for 2 seconds, that's going to mean quick. Okay, so it means that we would have another human-machine interface. For the assistive tool for the detection of early sign of cancer, for example, for the breast cancer, we would like to detect the so-called microcalcification, which is the tiny deposit of calcium in the breast in the X-ray image. So we achieve that by using fuzzy systems. For the cervical cell classification, we also have the assistive tool to detect cervical cells automatically from the pap smear image. This is assistive tool for Alzheimer's disease patient, in which we would take the brain MRI and we have the automatic segmentation algorithm. And at the end, we would come up with the segmented brain in 3D. Okay, and when we take a look at the volume of that, not just the volume of the whole brain, but also the volume of the so-called hippocampi as well, you can see that the shrinking of this hippocampi would be rapidly changed, right, when the patient has the Alzheimer's disease. And at the end, I would like to show you some of the platforms that have been deployed in real life. We have the so-called Simugency platform, in which we came up with a device that can measure 12-lead ECG, the blood pressure, oxygen saturation, the heart rate, and the pulse rate, also with the GPS location. We apply this device with different web apps for the patient, for the operator, for the ambulance, and also for the medical personnel. Okay, so they can keep track of the vital signs of the patients all the time. As we know that fall is a serious problem, particularly in elderly. So we have the so-called CMU fall detection platform that help the elderly in Chiang Mai and nearby. When the elderly falls, the device would send out the message so that the help would come in time. We also have the fire elephant, which is the IoT-based smoke detector platform that we install in the forest in Chiang Mai, so that it can send the message to us that there is smoke in that area. So the personnel who take care of the wildfire will go to that location in time, and it's not going to be widespread. The idea is that we would like to extinguish the fire as soon as possible. And that is going to be it for the final word. Okay, if you would like to look at some more of my work, you can go to my personal web page, or you may try to Google search or Scopus or Web of Science search for my last name, and you can see some more work. And for the real final word, I would say dream big, realize it. So let's collaborate. If you think that we can collaborate, please do not hesitate to contact me by the email that I show in my first slide. At the end, I would like to thank my colleagues and my students and the research funding agencies that help us come up with the nice research. Thanks to them.
Professor Nipon, thank you for watching the video. Finally, it's time to start the closing remark. Okay, I would like to invite Honorary Professor Kyungwoo Kang, Hanyang University. Please come to the here and give us brief closing remark. Please welcome Professor Kang with a warm round of applause.
Almost 4 hours, and the plenary session, 8 sessions, starting last field is general, and finally some laptop introduction. Oh my God, this plenary session is really long and tired. I admire you sitting here to listen to this all the plenary session. All the people, I asking to you, good job. A couple of days ago, the president of KITS, Lee Sang-soo, at University, asked to me whether I can do closing remarks. And I little bit hesitate. What time to me allow? He said to me, maximum 5 minutes. And as short as possible, if appreciate. So my remarks allowed is 5 minutes, but I can do 3 minutes. Okay, first of all and foremost, I would like to express my great appreciation to the excellent speaker from Rothschild, US, and despite in the COVID-19, here to New York Times to present Professor Fujiwara from Hiroshima University, and my good friend in the ITS Singapore. I really appreciate your contribution here to 20th anniversary of KITS. My deepest gratitude goes to all who people attended this conference and all the help to make it such a successful event despite of this COVID-19. Despite of this my short time, I have to be concluding remarks summarized in the 3 speakers. First speaker, Rothschild, my good friend is 20 years and dear good friend of Professor Xi'an, almost 30 years. Despite this time difference, we hours in about 1 o'clock in the morning in the Zoom meeting. It's crazy, so I really appreciate Villas. And not surprisingly, he talked about regulations and standardizations. He's working in the last 30 years in the lifelong devotion to the ITS TC204. I'm great appreciate his contributions. Second speaker, I personally very interesting subject is social acceptance of ITS. Despite his data is not fully developed, but I really like to see his future works. Finally, my good friends in the ITS Singapore, in the Japan and Singapore, we expecting to your contributions 2026 Kang World Congress. I really appreciate that part. And his Singapore, he mentioned about in the highly qualified data issues and quantum computing, artificial intelligence, and the big data. And he and I little bit agreed that we have to be careful about big brothers government is looking at the shoulder your privacy issues. It's 2 minutes? No, I'm not going to that much. Okay. I write a little bit, but let's keep it simple. Finally, my deepest thanks are, of course, reserved for the Korean Institute of ITS secretaries for their priceless contribution and for running this successful event. You have 사무국 직원들한테 빅 박수 한번 쳐주십시오. Really, finally, I really appreciate and admiring our interpreter, 통역사들. It's a huge variety of the issues. They did an excellent job. So another big pro to our contributor, interpreter, 통역사들한테 박수 한번 해주시죠. Thanks, enjoying your dinner, and hopefully you got a lucky prize after these sessions. Thank you.
Thank you, Professor Kang. Ladies and gentlemen, KITS International Plenary Session has come to end. Our sincere thanks to all our speakers. We would also like to thank everyone for participating in the session.